Recording. So today we're discussing practice exam 2 for Chem 113, Organic Chemistry 2. So let's start and let's look through each question. Okay, so in this case, we're asked to predict the major and minor product, clearly identify the major product, draw a mechanism, and draw a Newman projection showing how the major and minor product are produced. Okay, so first and foremost, this is an unstabilized ylid. And as a result, the unstabilized ylid will prefer to produce the Z alkene. So let's take a look. If we have an unstabilized ylid, the mechanism for the Wittig reaction, you can either draw the 2+2 or the addition followed by the collapse to make a betaine intermediate. Both are accepted. I'm going to draw the addition-based mechanism. So in this case, our nucleophile will add to the carbonyl carbon. From here, we'll generate this alkoxy species, which will then attack our phosphorus atom to make a betaine intermediate. From here, this betaine intermediate can then collapse via a retro 2+2 mechanism to give the corresponding Z alkene. Now, in terms of the two Newman projections for our major product, as we discussed in class, the addition of your Wittig reagent to your carbonyl carbon occurs to give an addition product that minimizes steric hindrance between your bulky groups. After rotation, we can redraw this Newman projection to show the resulting betaine intermediate formed as so. Let me check. Ah, yeah, this isn't a hydrogen. This is actually a methyl group. There we go. Sorry about that correction. So to showcase the Newman projection for this betaine intermediate, in this case, as we can clearly see, the two bulkiest substituents are on the same side. So when the betaine intermediate collapses, we'd get the desired Z alkene. In terms of the minor product, all we have to do is take all of our Newman projections and flip the position of the back substituents. So in this case, for our minor product, even though the actual addition is less favorable because we have these bulky substituents close together, when we look at the resulting betaine intermediate, we see something pretty interesting. First, we notice immediately that in the betaine intermediate, our bulky substituents are far apart. So this betaine intermediate is relatively lower in energy compared to the major product. So that's why when you have a stabilized ylide and you can see some equilibration before the betaine intermediate forms and collapses, you see more of this minor product. As we see, when this betaine intermediate collapses via retro 2+2 reaction, we end up generating the corresponding E-alkene. Does this example make sense to everyone? And this was discussed in the chapter 19 notes.
I don't remember that the minor product Newman projection being drawn in the notes. So I was really confused on the minor product.
This is the same Newman projection drawn for the stabilized ylide. And I would also look, I believe it's on the section for the Wittig reaction. We drew both the major and minor, and both of those are drawn in those two figures in the bottom of the note set for the page for the Wittig reactions. I can show you on the note set once we're done with this discussion, if that's okay.
Okay.
The main thing to keep in mind is that the only difference between the major and the minor Newman projection for this Wittig reaction are the position of the back substituents, whether you're funneling to the Z or E product. And that's based on the relative position of the substituents in each Newman projection. Does that make sense?
Yeah.
And I'll provide you the reference pages at the end of this discussion. Any other questions on this example?
Professor, is it okay if we like for the isopropyl if we put like the R on there?
That's fine. That's fine. As long as you identify what that R group represents.
Okay, perfect. Thank you.
Mm-hmm. Certainly. Okay, let's look at this case. In this case, we're asked to propose a synthesis of the following compounds, and the following starting materials are not allowed, but you can propose a route that uses these compounds as intermediates. Okay, so we're asked to prepare the following asymmetrical thioether. Okay, or sulfide to be more exact. So I'm immediately inclined to break these bonds. So retrosynthetically, I'm just going to arbitrarily break this first bond here. And we'll trace this back to some sort of sulfur-based nucleophile and some sort of alkyl halide. Okay. Now, this reaction will work just fine, but we're banned to use this starting material. Okay. So let's disconnect this further. And let's trace back this starting material to an alkyl halide and some sort of hydrogen sulfide anion equivalent. Okay. Now, the key point behind this problem is that if you run this reaction, so if you treat this alkyl halide and just treat it with sodium hydrogen sulfide, will this reaction work as drawn? Will we get this desired product as drawn? What's a central issue in preparing sulfides and preparing thiols? You'd get more than that product. If you ran this reaction as is, you would run into a substantial amount of polyalkylation, right? This is a common issue that we discussed when we talked about the synthesis of thiols and sulfides. So then, what is our fix? We had a proposed fix in order to promote and favor monoalkylation. And what is the trick to favor monoalkylation, or at least prevent self-reaction of our generated thiol? What's the workaround that we talked about in the note set when it came to the synthesis of thiols and sulfides? What is our workaround? The thiourea fix, exactly right. So in this case, we'd use thiourea. So we treat with thiourea and then sodium hydroxide, and that would give us only the desired thiol. From here, we can treat our thiol with any base. I'm just going to use sodium hydride, but any base would do. You can even use LDA. That would all work. And then we treat with our alkyl halide. And that would give us our desired product. So here's our two-step synthesis. I'm just showing you the retrosynthesis, both because it's useful for partial credit and because it helps you structure your thoughts and identify common patterns of reactivity and common synthetic equivalents. Does this example make sense?
Is it okay to go like the other way? I did a cyclohexane with the bromine instead of like a propyl with the
As
bromine.
long as you use thiourea, that's the main point for this question. You generally
Yeah.
can't make the sulfide directly from the alkyl. Sorry, you generally can't make the thiol directly from the alkyl halide without going through the thiourea. If you go through just sodium hydrogen sulfide, you're likely going to make a symmetrical sulfide instead. Does that make sense?
Yeah, I use thiourea. Just
Yeah, the other way is perfectly fine.
okay.
It's completely arbitrary, and there are two solutions actually to this problem.
Okay.
Or at least two conventional solutions. There are others, but this is the most common using what we've learned in the class.
Okay.
Perfect. Okay, so in this case, we're asked to propose a synthesis of the following compound from an alkyl halide, and your starting materials must contain less than 9 carbons and sulfur atoms. Okay, I see this sulfone. I'm going to cut off these oxygens. We can install them via oxidation. We definitely know how to do that. And what really stands out about this substrate? What really stands out about this substrate?
Symmetrical.
It's symmetrical, exactly right. So we can use that recognition of symmetry to break this down to a pair of identical alkyl halides and some hydrogen sulfide anion equivalents. I can draw them out just so that way we can see what's going on here. So here, because we have a symmetrical sulfide, we can just start with our alkyl halide and it almost makes itself in a way. So starting from our alkyl halide, we just treat with sodium hydrogen sulfide. And that in turn will give us the symmetrical sulfide. And then from here, if we wanted to make the sulfone, there are a few ways. You can do hydrogen peroxide, 2 equivalents. You can use chromium trioxide, any of the oxidation methods mentioned in the book. Keeping in mind, you have to use an excess of oxidizing agent in order to avoid stopping at the sulfoxide. Does this example make sense to everyone? Any questions on this synthesis problem?
Can you scroll back down so I could see the top part, please?
Sure.
Thank you.
There we go. Any other questions I can address? Okay, so let's keep going then. So in this case, we're asked to predict the product and draw a mechanism. So in this case, we have an alkyl halide reacting with a carboxylate anion. So our anion will attack and displace our alkyl halide, and that in turn gives us our desired product. Keeping in mind, this is an SN2 reaction, and thus it occurs with inversion of stereochemistry. Any questions on this example? Okay, let's look at the next problem. So in this case, we have a tertiary alkyl halide. Do tertiary alkyl halides give substitution generally? Do tertiary alkyl halides give substitution products?
No.
No, we'll primarily see elimination. In this case, I only just want to see a representative mechanism for the elimination. If you want, you can even draw a Newman projection to justify your predicted product. You also clearly have the potential, because we have 2 protons, to get the other alkene geometry. And you can also get the other regioisomer, where if you pull off this other proton. So as you can see, because we have a tertiary alkyl halide, we get a range of elimination products. As long as you put at least a few of the elimination products and you show this E2 mechanism, you'll get full credit. Does this example make sense to everyone? Any questions on this example? Yes, there are at least 4 products. 2 of the regioisomers and then each of the stereoisomers. As long as you list at least 2 of the elimination products, you get full credit for this question. The main thing this problem is trying to test is this recognition that the Williamson ether synthesis and the synthesis of esters and carboxylate derivatives only works efficiently if your alkyl halide is primary or secondary. If it's tertiary, you'll see an appreciable amount of elimination. Does that make sense? Any other questions on this example? Okay, let's keep going then. In this case, we're asked to predict the product and draw a mechanism for each step. In the first case, we have an allylic alcohol reacting with an allyl chloride under slightly basic conditions. So for our first step, carbonate will pull off a proton. I'll draw this with equilibrium arrows just to show we get just a little bit of the alkoxide ion present in solution. From here, we now have an alkyl halide. In this case, it's an allyl halide that can react via an SN2 reaction. And from here, we get this corresponding allyl alcohol. This is A. After heating, again, looking at our numbering, so in this case, if we try to heat this compound, what will happen? Will anything happen? Can anything happen in this case? So we talked a lot about concerted rearrangements, and this problem is really designed to test if we can recognize the substrates for these rearrangements and if we understand and we're fully comfortable with the conditions for these reactions. So looking at this substrate, do we have the proper setup for a 3-3 rearrangement? Exactly right. As a student's noting, this substrate can't really undergo a 3-3 rearrangement. It doesn't have the correct relative arrangement of substituents. So in fact, you're going to heat this and nothing will happen. We just would be able to re-isolate our starting material. Perfect, perfect. No, we won't really see a hydride shift. The main thing this problem's trying to test is to make sure people can recognize when a reaction will occur, even when they see conditions that look like a typical condition for a 3-3 rearrangement. Does this example make sense to everyone? So one thing to keep in mind, no reaction is a perfectly reasonable thing to say if no reaction will occur. Any other questions on this example?
What would it look like if it was a Claisen reaction?
So we'll actually see a few examples of this, but if you were to try to alkylate and enolate instead, and you can get selective O-alkylation, this substrate has the exact proper arrangement for a 3-3 rearrangement. So when you heat this substrate, it'll undergo a classic Claisen rearrangement and will generate the alpha allyl ketone. Does that make sense to everyone? Does everyone see the subtle difference between these two substrates? I found this is a good time efficient way to test if people understand the mechanism for a reaction and understand the substrate requirements for a reaction without having to draw the mechanism fully.
Where's the arrow number 3 going? Or not number 3, but the bottom.
It's going to form a bond between these two carbons.
Oh, okay.
Draw this a little bit closer so that way it's easier to see. Looks something like this. Does that make sense? Did that answer your question?
Yeah, thank you.
Perfect. Okay, so let's keep going now. In this case, we're asked to predict the product and draw a mechanism for each step. So in the first case, we're treating our starting material with sodium cyanide. So if we have a ketone and we're treating it with sodium cyanide, our nucleophilic cyanide equivalent will attack our electrophilic carbonyl carbon, and we will generate the corresponding cyanohydrin. Treatment of our cyanohydrin with lithium aluminum hydride will reduce our cyanohydrin all the way down from the nitrile directly to the amine. So lithium aluminum hydride will donate an equivalent of hydride. And then from here, a second equivalent of hydride can be donated to further reduce down the nitrile. And then from here, when we quench with water, we're just going to protonate the anions. So the alcohol doesn't really do anything just because we're under basic conditions.
Is it fine to, I protonated the alcohol at the very beginning.
That's fine.
Okay.
That's okay. The
And
reason
then-
why I didn't is just because as drawn, there's no protic source yet added. So
Yeah,
it will be protonated once we add water.
okay.
Does that make sense?
Yeah.
If you wanted, you can show this alcohol protonating your amine, but when you quench with water, any anionic species generated will be quenched out. So in effect, just like we showed in the chapter 20 note set, you can readily prepare amines from ketones via addition of sodium cyanide to make the cyanohydrin, followed by reduction of the nitrile. And I'll scroll up just for everyone's reference. Does this mechanism make sense to everyone? Any questions on this problem? Any questions I can address? Oh, yes. This methyl wasn't showing up. There we go. Any other questions on this example? Okay, let's keep going. In this case, we're now asked to predict the product from each step of the following reaction sequence and draw a mechanism. So we have a nitrile and a Grignard reagent. So Grignard reagents add to nitriles just like they add to ketones and other electrophilic carbonyl functionality. So our Grignard will add in. From here, we'll get our imine anion. And now this is where something interesting happens. When we quench with water, first we'll protonate this imine. And now from here, this imine is not particularly stable. So now water is going to go in and it's going to attack our imine. I think I'm going to show a protonation step first to get a more plausible intermediate. You can show the attack directly, but I think it's far more plausible for us to protonate the imine first. Because now it's activated and really any nucleophile will do the trick. From here now, we're one proton transfer away from being able to kick out our amine. So we're going to engage in a proton transfer. And from here, we now have this wonderful leaving group in the form of ammonium. So we can kick out our ammonium ion. And that gives us our desired ketone. We still have one more step to engage with. We still have to deprotonate our ketone as a cleanup step. And from here, we now have our final desired product. Does this mechanism make sense to everyone? We've covered this extensively in the chapter on reactivity of nitriles and the reactivity of imines under aqueous conditions. Does this example make sense to everyone? Okay, let's keep going then. In this case, we're asked to predict the product from each step of the following reaction sequence and draw a mechanism for each step. So in this case, we have a primary amine and we're treating it with thionyl chloride. So this looks like a textbook amide dehydration. So for the first step, our nucleophilic amide will attack thionyl chloride using the nucleophilic oxygen atom. From here now, thionyl chloride will collapse and will kick out an equivalent of chloride. From here, we can now pull off a proton and kick out our wonderful activated leaving group. This in turn gives us our protonated nitrile. We'll use chloride. You can also use an equivalent of amide. All would be fine just to pull off this proton. And then a second deprotonation step frees up our desired nitrile. So that's the end of step 1 with thionyl chloride. So that gives us the desired nitrile. Does that first part make sense? Any questions so far before we move on to the next part?
Isn't this the mechanism that we just did today? Or
Not quite. Not quite. This was covered in chapter 20. And
is it similar to the one we did today though with the SOCl2?
Yes. It's very similar mechanistically, except this time, rather than displacing your leaving group with an external nucleophile, you can think of the lone pair on your amine as an internal nucleophile that puts down a lone pair and displaces your leaving group.
Okay, thank you.
Does that make sense?
Yes.
So the main reason why I'm drawing the distinction is that we don't lose our amine nitrogen in this mechanism. Instead, we dehydrate and lose an equivalent of hydroxide or water in this reaction. Does that make sense? Perfect. So when we treat this nitrile with strong acid, these are hallmark conditions for us to make a carboxylic acid. So in our first step, we're going to protonate our nitrile. Then water will attack our nitrile at the electrophilic carbon. From here, we're going to do a series of proton transfers, both to activate our imine and to free up a lone pair. From here now, we now have a highly electrophilic imine-like species that can be attacked with a second equivalent of water. From here now, we're almost done. We're again going to engage in a series of proton transfers. We've now freed up a lone pair on oxygen, and we've made an activated leaving group in the form of ammonium. From here, we can kick out our leaving group, and that gives us our desired carboxylic acid. To free up our lone pair and to get a neutral isolable product, we'll just pull off our last proton. Does this mechanism look familiar to everyone? Have we seen this mechanism before? Any questions on this example? Okay, let's keep going then. So in this case, we're asked to propose a synthesis of the following compounds from the indicated starting material. Okay, that seems straightforward. Okay, so first things first, this is an enamine. And I know I can make an enamine from a ketone. So I'll trace this back to the following substrate. Now, how can I make an alkene when I have an aldehyde? How do I make alkenes from aldehydes? What reaction do I use? Keeping in mind, notice how we've added a carbon, right? How do we add carbons while preparing an alkene from an aldehyde? What reagents do we use generally? If you use a Grignard, you'd have to do an elimination step. What's a more direct method to prepare alkenes from ketones and aldehydes? A Wittig reaction, exactly right. So we can trace this back to the following substrate and methyl triphenylphosphonium bromide. Oops. There we go, which looks something like this. Now, in terms of our forward reaction, we've traced back to our desired starting material. Why does this Wittig reaction work so well? So if we treat this substrate with methyl triphenylphosphonium bromide, why does this reaction work? That's just a counter. The bromide is just floating around in solution as a counterpart. Because remember, this is positively charged, so you have to have a corresponding counter anion. It's not particularly important. I'm just noting it for accuracy and completeness.
Okay, because in our other examples in the notes, you just put the negative charge on the carbon, like a lone pair, and it made it negative.
Yes. So you typically make, well, let me elaborate on this for a moment. So let's suppose that you start with just a normal alkyl halide, right? you treat it with triphenylphosphine and you'll get methyl triphenylphosphonium bromide. If you treat with butyllithium or any other sufficiently strong base, that would give you your Wittig reagent. Does that make sense? So for the purposes of retrosynthesis, you can just draw the Wittig reagent, but I just want you to note this is derived from methyl triphenylphosphonium bromide. Does that make sense? Did that clarify your question?
Yes, but is there still like a is it called an ylide? Like, is that where it's negative charge?
This is the ylide where you have a form where you can place a negative charge on the carbon. Before
Okay.
with base, there's no negative charge on the carbon.
Okay. Okay,
Does that
yeah.
make
So
sense?
it's just, so it's not really saying that it's like that the bromine is like attached to that
No,
molecule anyway.
the bromine is just a counter anion.
Okay, that makes sense.
Yeah, just like if you have like sodium chloride, chloride's just the counter anion. Yeah, I'm just showing you if you're asked to prepare this ylide from, for example, methyl iodide or methyl bromide, it can be done. And this is the sequence to prepare this ylide. Just as a refresher. Now, this is a really important idea. When we run this reaction, why does the aldehyde react preferentially? In general, which reacts first, the ketone or the aldehyde? In general, what reacts first? Aldehydes, yep. So we get the desired Wittig reaction. We don't have to be concerned with ZE selectivity because, as you can see, this alkene doesn't have any unique stereochemistry. And then from there, if we wanted to prepare this enamine, we just use our corresponding secondary amine and catalytic hydrochloric acid with heating. From that, we'd form the desired enamine, which always preferentially forms on the least substituted position. As we talked about in lecture, an enamine is an equivalent of a kinetic enolate. Does this synthesis example make sense to everyone? Any questions on this example? If not, let's keep going. So in this case, we're asked to prepare the following compound from this starting ketone. So first, we can break off this acetal to get our parent ketone. And of course, we can add any alkyl group to the beta position of an unsaturated ketone using a organocuprate. Okay, so in a forward sense then, we take our unsaturated ketone and treat it with dimethyl cuprate. That will give us, and we'll quench with water after, just as a quench step. That gives us our 3-methyl cyclopentanone. Then from here, we just treat with the corresponding ethylene glycol and hydrochloric acid or toluene sulfonic acid and heat, and that generates our desired acetal. This problem is really designed to test your understanding of synthetic sequencing. We have to do the organocuprate reaction first, because the moment we make the acetal, the alkene is no longer reactive with common nucleophiles. Does this make sense to everyone? Does this example make sense? Okay. In this case, we're just asked to do some product prediction. So we have a thiol and an unsaturated ketone. So we have a choice between 1,2 or 1,4 addition. Where do thiols generally add? 1,2 or 1,4? Thiols, which are traditionally considered soft nucleophiles, where do they add? What do we think?
1,4.
1,4, yep. So that will give us substitution at the beta position. Okay, what about Grignards? Do they add 1,2 or 1,4? Grignards, which are typically hard nucleophiles.
1,2.
1,2. Okay, so we end up making this alkoxide species. And what does trimethyl chloride do? It protects the alkoxide as a silyl ether. Exactly right. This is an example of these tandem reactions that we mentioned in lecture, where you can make an alkoxide species and then immediately trap it with an electrophile. Does this example make sense? Okay. We're treating an alkene with permanganate under acidic conditions. This is a close relative to ozonolysis in terms of what products it generates. So we cleave our carbon-carbon double bond and we generate the corresponding carboxylic acid or ketone. Yeah, you don't need to know the mechanism for that reaction, as it's similar to the ozonolysis mechanism in that it's almost like you end up with dihydroxylating the alkene and then that cleaves. But no, you don't have to concern yourself with that particular mechanism. Since in reality, most of the times you want to do this transformation, you're better off doing ozonolysis with an oxidative workup. Any questions on these examples? Not necessarily. If you do an oxidative workup, you'd get the carboxylic acid. Just like what we discussed in the chapter 20 note set. If you use dimethyl sulfide, you would get the aldehyde. That is correct. Any other questions on this? And that statement in the chat is correct. Okay. So in this case, we have when I exported the file, there was a little bit, something got cut off. Let me check just to make sure I'm drawing the structure correctly. This is just a quirk of OneNote. Let me find it. Give me one moment. Yeah, I'm just making sure, just so that way. Sometimes OneNote likes to do weird things too. Ah, this is a good one. This is a very good reaction, as it combines two things that we've learned. So if we treat an amine and an aldehyde with catalytic acid, what are we going to make? What are we going to make? An amine, aldehyde, what do they react to make? Not quite an amide, but an imine. 1, 2, 3, 4, 5. So we get a 5-membered imine. Okay. And then just like, yes. In this case, you're not asked to draw the mechanism. So I'm just highlighting the patterns of reactivity for these product prediction problems. Yes, of course. If you wanted the full formal mechanism, we'd protonate the aldehyde. The amine attacks. And we'd have a series of proton transfers. Just to be clear, for these problems, you're not required to draw the mechanism. And now, once you have water as your leaving group, you can just kick out water, and that gives you the corresponding imine. Now, just like ketones, what happens when you treat an imine with a reducing agent? What happens when you treat an imine with a reducing agent? Just like ketones, what happens? We have this electrophilic carbon. What happens when you treat this imine with a reducing agent? Of course, hydride will reduce the imine down. And that gives us the corresponding amine. Does this example make sense to everyone? It's just like a ketone, right? Just like you can reduce a ketone, you can reduce an imine. It can either it will pick up a hydrogen at the end of the second step, either during the quench or from an acidic species in solution. Does that make sense? Perfect. Okay, let's look at this next case. If we take an amide and we reduce it with lithium aluminum hydride, what product do we get? When we reduce amides down, similar to nitriles, what product do we get when we reduce an amide? If we reduce an amide down, do we get an amine or an alcohol? Do we get an amine or an alcohol? What does the class think? An amine, yeah. As we discussed in the reactivity of amides and nitriles, reduction of amides and nitriles yields the corresponding amine. Any questions on this example? Okay, let's look at an oxidative process. If we treat a benzylic position with potassium permanganate and an H3O+, what happens to this benzylic position? We convert it from a typical alkyl group into what functionality if it's primary? What functionality do we get under these allylic oxidation conditions? Some would call them exhaustive oxidation conditions. The carboxylic acid, exactly right. This is a useful method for preparing aryl carboxylic acids. Okay, perfect.
Oh, so are we talking about like the proton is primary or?
No. This carbon.
Okay.
Right? Do you see how it only has one substituent, the aryl group?
Uh-huh.
And we have 3 hydride equivalents. So we can oxidize up this carbon all the way to the carboxylic acid oxidation state.
Okay. And if it was secondary, it would be an aldehyde?
It would be a ketone, but yes.
Okay.
Right, because if it was secondary, for example, we would only be able to oxidize it up to the ketone before it stops because we have another substituent on the opposite side.
Oh, yeah. Okay.
Does that make sense?
Yes.
Perfect. So with that, we completed the exam run through. Whoops, one moment. So let's stop the recording.